Good morning, everybody. It is very nice to be here. First, I would like to thank Steve Awodi, Thierry Coquin, and Vladimir Voivodsky for organizing this program, which is very exciting. And also to thank the organizer for inviting me. I have tried to prepare this talk since about a week and sort of failed because there was always something more interesting to do, like discussing with the participants here. So my talk will not be very formal. It will be more about things that we may do collectively than things that I have done. First, I would like to make a list of the things that we would like to do in homotopy type theory or univalent foundation. My list will not be exhaustive, certainly. But it's kind of good to look at it. First, we would like to do higher category theory. Well, this contains also category theory. Yes. We would like to do higher topos theory. Maybe have a development of higher operads. And of course, operads. Stable homotopy theory. We would like to do a good Willy calculus. We would like to do homotypical algebraic geometry. And possibly many more things. This may look to you like a wish list for Christmas. Maybe it is.
Was it coming Christmas?
That would be marvelous. I will say a few things about higher category theory, maybe a little bit about higher topos theory, stable homotopy theory, and good Willy calculus. I hope I will have the time to get to the last part. But let me start with higher category theory. Well, many people in this room, including myself, have thought about the problem of developing higher category theory in homotopy type theory. Maybe I should say that I am far from being an expert in homotopy type theory because I'm not really knowledgeable in type theory. I'm learning it. So it's very good that this book project, for example, that you have, I'm looking forward to read the book so as to learn type theory and homotopy type theory properly. But discussing with people, I have developed a certain feeling that I maybe understand something about the type theory and homotopy type theory. It's more sometimes more a feeling than an actual knowledge. So I will not present what the things in the language of type theory. Unfortunately, I cannot do that. So maybe many people in this room are going to be able to do that. So the first thing we need simplicial types. This is very clear. And why do we need simplicial types? Maybe I should recall a little bit why we need simplicial types before getting involved into how to handle this problem. So I recall that a simplicial object in a category C is a functor. Let's say x from delta contravariant functors on the category delta to the category C. Just to fix the notation, I'm going to use delta 0, delta 1, and sigma 0 for the operators. I'm using Greek letters. And this is just dual to the operators. D0, D1, S0, etc. So now what is a category? If you take the nerve of a category, you get a simplicial object let's say little c is a simplicial set n of c satisfying the Siegel condition. And one way to express this condition is the following. You look at the inclusion lambda 1, 2 in delta 2 is the horn defined by removing the face opposite to vertex 1. So this is lambda 1, 2. And it's included, of course, in delta 2. And one way to state the Siegel condition is to say that the map, the canonical map, from x to delta 2 to x lambda 1, 2, the restriction map. So you exponentiate the simple object by delta 2, and you exponentiate it by lambda 1, 2, and you just say that this map is an isomorphism. The Siegel condition is not expressed this way, in this manner, usually. The difference is that here it is expressed internally. In other words, we are using exponential in simplified set to express the condition, and therefore we can get away into expressing that xn is like equivalent to whatever, etc. So it's a kind of a simpler way to express the condition. And for simplicial space or simplicial types, we would like this map to be an equivalence instead of being an isomorphism. And in this case, this notion is called a Siegel space by Recht. It's called a Siegel space. If you take a simplicial space and you ask that this map is an equivalence, then it is the notion of a Siegel space. But for us, we could call them a category. Well, there are maybe many possible terminology about that, but let me call that a category, that a simplicial object is a category. Potentially, we may define, if we have simplicial types, we could say that a simplicial type, if we had them, is a category if this map is an equivalence. That would be the definitions of a category. That would be an infinity-1 category. There are other conditions that can be put there, because there is a notion of a complete Siegel space, and that's the univalence condition. So how can we express the univalence condition? Well, we need to construct a simplicial object which model the notion of an arrow with a left and a right inverse. So we just create this. So you glue two triangles in this manner. So you glue delta 2 with delta 2. You can see this picture inside delta 3, because you take the zero face of delta 3. I mean, delta 3 looks like this: 0, 1, 2, 3. And you take the zero face, which is here. and which is opposite to vertex 0, and you take the face number 3, which is opposite to 3, so you get this thing. Okay, and what you see is two triangles that are connected in this manner. I mean, like this one. I mean, well, they don't look like this, maybe, but that's what happened. Yes?
Do you want two arrows on the parallel sides to be different directions?
Oh, yes, right. Thank you. Yeah.
Okay. And then do you want delta 1, or delta 2, delta 2?
Um,
The right where next to it. No, just in your formula.
Here?
One step up?
Oh, here?
Yes.
Okay. You want to define the inclusion?
No. Do you want there delta 1 union with delta 1 or delta 2 union with delta 2?
No. I want delta 1 union delta 1. I will come back to this in a moment.
Oh, okay.
I will come back to this in a moment. In this picture here, what we have is this, is 0, 1, 2, 3. And we have this, and this, right? Now, I want to take this edge and squeeze it to a point. Okay? And I want to take this edge and squeeze it to a point, so to get this picture. So there is an identification here to a point, right? And these two edges are what I want to squeeze to a point. So they are 1, 3, and 0, 2. And here, let's say delta 0 union delta 0. And I take a push out, and I get this picture of this diagram. Okay. And mapping this into a simplified set, or any simplified object, is like picking an arrow in X with a left and a right inverse. Okay. And now, definition, a category X is univalent. If the map, the canonical map, the diagonal map from X to X to the J is an equivalence. So this is really the same thing as the notions of a complete Segal space of Charles Reck, up to a change of terminology. Okay. Okay, now maybe some people here would like to call that a pre-category and to call that a category. Okay, that's a matter of debate. The reason I prefer to call that a category is that a groupoid is a special case of that. I like to think of groupoid as special case of categories. So I'm sorry?
Can you expand on that? How is the groupoid more a special case of that than that? I guess just groupoid is an inclusion of that.
Okay, let me define. Well, a simple shell, whatever, a simple shell object X is a groupoid. If the map the maps from x to the delta to x to lambda I2, so you don't have to pick I equal to 1 as in this case, but it could be, it's also true for is an equivalence. For I into 0, 1, 2. So, and then you can define what is a group. A monoid if x0 is actually pointed and equivalent to 1. So you maybe have a base point P. Well, let me just write P equivalent to 1. Okay. So there is a notion of a group, of a groupoid. Now, why is this important? Of course, many of you are aware of the importance of these. But let me recall, maybe I should start here. Given a map between two objects, maybe in homotopy type theory, this map should be a fabration, or it should be turned into a fabration. We can associate to it a groupoid. Which is just this simple object. And I like to call this the Cech groupoid of F, because in computing Cech cohomology, you take a covering A of a space, and you use this simple object to define the cochain complex of Cech cohomology for corresponding to the covering A. So we may call that the Cech groupoid of a map. Now, this defines a functor from the category of maps to groupoids. Cech. The Cech functor. And this functor has a left adjoint, which is called B, the classifying space of a groupoid. So it takes a groupoid into it's a homotopy colimit, if you like, BG, but equipped with the map, the structure map from G0. There's a canonical map from G0 to the homotopy colimit of this diagram, and so that produces a map the other way, right? So, and this B is the left adjoint to the Cech groupoid. And now, a basic result is that if you replace map, the category of maps, I mean, map is the category whose objects are maps and morphisms are commutative square. If you replace maps by epimorphism, then you get actually an equivalence. So the category of groupoids in type theory, of course, I mean, with univalence and all the axioms, I mean, I'm now in this universe, is equivalent to the category of maps. EP, I'm sorry, of epimorphism would be. I'm sorry?
Isn't the Cech object for an isomorphism contractible? Okay, so it's not contractible, it's equivalent to, if I have an epimorphism A to B,
Yeah.
and I build this Cech gadget on it,
Yeah.
let's suppose that it's, let's suppose it has a section.
Yeah.
Not just an epimorphism, but actually it has a section.
Okay.
Then from this section I can construct a homotopy, a simplicial homotopy. Simplicial homotopy equivalence between the Cech object and B.
Well, let's look at a special case of that and check what happened, because I understand your question, and my impression is that the answer is not, but okay. Let's take the special case where we fix the domain A to a point, because in the category of epimorphism, you have the case where the I'm sorry?
Let's fix B to the point.
Yes. But in any case, if I fix A to a point, what will happen is that I will have a retraction here, which you may consider, or you don't want to consider it as a section. Okay. But, yeah.
No, other way around. If I fix B to a point.
Yeah. So, I mean, are you sort of questioning the validity of the result, or?
Yes, I suppose so.
I mean, I could have made a mistake, but I'm quite sure this is correct. Yeah.
The category of groupoids, the homotopies in there are pointwise homotopies, not simplicial homotopies.
As simplicial object, the notions of equivalence is pointwise. Exactly.
Yeah, so because I was thinking if you are collapsing this
Okay. That's not the same kind of notions of equivalence. I see. I see. I see. Yeah. 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 I see. Right.
Pointwise meaning what in this case? Degree-wise?
Yeah. Yeah. Degree-wise. Okay. That's open a discussion, because if I call this a category, I would like the equivalence between the categories to be the right one. And here they are the pointwise one. And we know that an equivalence of categories does not, in general, induce a bijection between the objects. But here, this is what's happening. So, okay, we will have a, maybe this should be called a pre-category. Okay. And would you call the others a pre-groupoid then? Because if we call the others a pre-groupoid, the notions of groupoids collapse. The only groupoids are just objects, which maybe you like.
I mean,
Okay. 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 Look, I can make the change now. Okay. A pre-category, a pre-groupoid. Okay. 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 But a group is a pre-groupoid such that. Okay. You won't call that a pre-group, right? Okay. 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 And now this is okay?
yes, I guess so.
Okay. Okay. So a special case where A is 1 you look at the epimorphism. So these are pointed connected spaces, because an epimorphism from a point to B means that the point is surjective, and that means that the space is connected. And of course, up there, what you have is omega B, the loop space, and so you have this group. The loop space becomes a group. It has a group structure. And so this equivalence between here specialize to the case of an equivalence between pointed connected spaces and groups, which of course is a classical equivalence. Okay. The reason I'm stressing that now is that this simple object here, the Cech complex, is infinite. In general, you cannot stop. You have to take it all in order for this theorem to be true. In other words, it seems that if we want to do some kind of elementary theory of infinity-toposes, apparently we would have to take infinite object to express equivalence relations. And I'll come back to that in a moment. Maybe I'm going to say a few things about how you can do category theory with in this setting. Again, this is known to many people in the assistance, but sometimes it's not bad to recall. So I will just recall the definitions of initial object. So if X is a simplicial set, a simplicial object, then and if you have a point A in X, then you can construct another simplicial object called X over A. And I will recall this construction. First, you construct a simplicial object called decalage, dec X. And dec Xn, roughly speaking, is just Xn plus 1. This is because there is a canonical inclusion of n into n plus 1. And actually, n plus 1, this endo functors, this is a monad. On delta. That's an endo functor. This is the successor. Maybe we could call it the successor monad. So there is a unit map from S to S delta n. That's just the inclusion of n into n plus 1. And there is also a map from S squared to S, satisfying all the conditions of a monad. And the decalage of X is just composition with this monad. In other words, formally, dec X is defined to be X as a simple shell object composed with a successor. I cannot lift this blackboard. Okay, I should move to. So, intuitively, if you have a category and if you do dec of a category, of the nerve of a category, actually this is like, I should say the dec of the nerve of a category is the nerve of another category, which you could call dec C. So one way to understand these constructions is to understand how you can do it on the category. So the objects of dec of a category C are just the arrows. Of C. And an arrow between two arrows. There will be an arrow between two arrows only if these two arrows have the same codomain, and then it will be a commutative triangle. So actually, we could say that dec of C is a coproduct over, the photo at 11:30. Okay. But okay. So dec of C is actually the union over all the objects of C of C over A, just the disjoint union of all these categories. So it contains in it all these slice categories, and this is the same for this simple shell dec, and you can there will be a map from dec of X to X, which is just dual to the inclusion. I mean, since S is a monad, composing with S is a comonad because of the contravariance of X. And so this is the co-unit of the comonad dec. And if you take now one point A of X, and you take the pullback, you can define the slice simple shell object as just the pullback. Okay. I'm beginning to worry about something in my description. Yeah, yeah, that's true. Okay, so okay. This is like this map here is like the domain is like H, if you like. So that's the domain map. And now there is the codomain, which is in 0, in X0, because all these arrows have the same vertices. And so this is the codomain. And now I'm taking the pullback. So I'm fixing the codomain in this. And now there will be a canonical map from x over a to x over a to x. There is a canonical projection. This is just like forgetting the base. And now we are ready to say what is an initial object. It's one way to do it. You say that A is initial if this map is an equivalence. If it's an equivalence, then A is initial. OK. So we can do category theory because if you read the book of MacLean, everything is based on the notions of initial object. As long as you can define the notions of initial object, the rest comes. I mean, it's a bit an oversimplification. OK. OK, now I come to something a bit more philosophical for a while.
Can I interrupt you and ask you
Yes.
about that? You're working throughout with simplicial objects. The X
Yeah.
is supposed to be a
Yeah.
simplicial object. So I wonder if your proposal for doing this in homotopy type theory
Yes.
is that these objects X should be objects of the type theory, regarded intuitively as simplicial objects, or that you would make a simplicial types. You'd be working in simplicial types in the type theory.
It's a good question. I hope I will be able to answer this in a moment. Yes. I would like to make an observation about the state of affair, so to speak. Normalization is very important in Martin-Löf type theory, and I would think that it's very important maybe in constructive foundations of mathematics. But Martin-Löf type theory was extended by adding univalence It was extended by adding higher inductive type. Maybe another kind of extension is adding truncation. And if you look at normalization, then, OK, Martin-Löf type theory is normalized. This we don't know. Maybe we will know tomorrow. I don't know. This we don't know. And this we don't know yet. But I apologize for not writing in the alphabetical order here. Have done a lot with homotopy type theory, with univalence and inductive types and truncation. They have done a lot without using normalization. So they computed by n of Sn. They computed by n plus 1 of Sn. For every n. There is Allenberg-MacLean spaces, Freudenthal suspension. James construction. And this thing seems to be just growing. And it is quite amazing because it shows that Mathemtics type theory with these axioms is a very powerful system for proving things. Now, I don't know what is your view, but the univalent foundations has at least two goals. Maybe one of them, maybe it's the initial goal of Vladimir, which is to provide a formal language for higher mathematics with proof constructed and checked by computers. You maybe, I don't know if this is correct, the correct goal, but maybe this is your initial motivation. And another goal is to have a constructive foundations of mathematics. And these two goals are connected. It's clear from this program. They are very closely connected. However, they do not completely depend on each other. They are kind of independent. And from maybe my point of view, maybe this is from my side, I very much like the practical goal of the Univalent Foundation program, which is to create a tool which is really useful for mathematicians. And this usefulness does not seem to depend on normalization. The proof is that what they did. Okay? Of course, eventually, if we can have normalizations for univalent, we'll make progress on the foundations and maybe progress also on the practical side. But we should not wait for normalization. We should just move ahead. So what I would like to suggest is to axiomatize simplicial types instead of constructing them. Until now, it seems that what we have tried to do is to construct simplicial types. And this is tricky. I don't know if there is a good solution for that. Maybe there is. Maybe we will find a marvelous solution, or maybe the new language proposed by Vladimir will provide a solution. I don't know. But we don't need to wait. We could just take homotopy type theory as it is now and axiomatize simplicial types. So this is what's toward an axiomatization of simplicial types. I do not know which axiom to put there exactly. I know some axioms. There are things that I would like to be put as axioms, but I do not know. I do not have a complete axiomatization to offer you. One way to tackle this problem is to just start using simplicial type axiomatically and try to prove things about categories, higher categories, and etc., using these simplicial types. And as we develop the proof, we will meet some obstacle of things that we cannot prove. Well, when you cannot prove, put it as an axiom. As long as the thing is true in a model. If we have a good model, we know that this is not wrong to make it true, so put it as an axiom. And collect axiom like this for a certain time, and maybe eventually we will find a simple axiomatization, hopefully. But even if we don't find a simple axiomatization, it does not matter that much. What about having, let's say, 20 axioms? Is this a large number of axioms? 20 axioms? No. Hilbert axiomatizations of Euclidean geometry has 20 axioms. But with computers, we could have 100 axioms. I mean, I hope we don't need 100 axioms. But there is the number of axioms. Of course, beauty in mathematics has something to do with simplicity. And if you have a small number of axioms, that would be very nice. But from a practical point of view, I feel that we may just move ahead and add axioms as we discover them. Okay, so what are the axioms that we may put? Okay, so let's analyze a little bit. Suppose that E is a topos. I'm actually a category theorist, so I like to think in terms of topos. So, but it could be an infinity-topos if you like. And then we can construct the simple object in E. Just the simple object in E. This is a grothendieck topos, simple object in E. And then we have the constant functor from E to which associate to an object the constant simple object, the constant presheaf with value in E. Okay, so constant x or maybe S n is just S. Okay. Okay. And and then there is collections of adjoint functors related to that. The constant is right adjoint to the co-limit functor. There is a co-limit functor, which is just the right adjoint to the constant functor. Okay. And the constant functor is left adjoint to the evaluation at 0 functor. Evaluation at 0. So a simple object has a 0 object, and so just evaluation at 0. And evaluations at 0 is the same thing as something called the co-skeleton 0. This is left adjoint to co-skeleton 0. So we have this sequence. Co-skeleton 0 is important because co-skeleton 0, let's maybe check. This is like inclusion of E in E to delta op. So these two here. The E is included in two ways into simple object. One is the constant presheaf, and the other is co-skeleton 0. And this co-skeleton 0 is important because co-skeleton 0 of a set S at n is just S to the n. So it is, if you like, the Cech complex of the map from S to 1. In other words, what I want to say is that co-skeleton 0 is the basis for constructing the Cech complex. It's just for the map from S to 1, but if you do it relative over a base, it will be this Cech complex. You can relativize it, and it will be. Okay, so but what about simple cell objects themselves? Now, there is something very well known in topos theory, is that this category is the classifying an interval. In other words, as an extension of E, you can see it as an extension of E with the constant. You have extended universe. You have a certain universe, a topos E, and you go to simple cell object. You have extended the universe. But this extension is about adding to E an interval object. And this interval object is delta 1, is the simple cell object delta 1. And delta 1 is an interval. A strict interval. Okay. So what is it, what kind of axiomatization I want to propose? I come maybe, okay. Maybe I go. Okay. Okay. Yeah, what is an interval? Okay, I will try to say what is an interval from the point of view of homotopy type theory. Okay. First, the interval I is in H set. It's kind of surprising. It's almost repulsive. You say, no. Okay, okay. But it is. In the end, an interval is an element in H set. Second, I is equipped with a linear order so linear means that it is total. In other words, you have A, you have X, B, yes. D this is, maybe it's called total in some, but in English I think we say linear order. Okay. And third, you have minima 0 is a minimum and 1 a maximum. And 4, 0 is different than 1. And that means that 0 equal 1 imply false, right? I mean, so the 2 points are distinct. The picture is just that, right? That's the interval.
May I ask a question? Yeah. So does number 4 hold for real numbers in type theory? No. That number 4 is a bit constructively is a bit strong.
Well, no, well, it means that the equalizer
D, number 4 is D, yeah.
number D, yeah, but we are in H set.
Well, you know, I don't think it's true for the real numbers constructively. But this is totally different from the real numbers. It has nothing to do with the unit interval of the real numbers.
Well,
It's a formal. It's a formal interval about which we know nothing except that. So we cannot even name a point in the middle because there is no name for it. And okay.
So it's the higher negative.
Yeah.
Axiom D is also not very constructive.
That's what we were just saying.
yeah.
What is not very constructive?
The one that is total. That is totally ordered.
I mean, it is constructive, but it's false.
No, look.
It's false for natural, or rationals, right?
But it does hold for the
Yeah. So the axiomatizations maybe you help me. The axiomatizations I think about is that we take a context, we introduce a context with that, and you work within that context. So if you work within that context, it means that you have an interval satisfying that. It's an H set.
Is bool an interval?
I'm sorry?
The discrete, is bool an interval?
Yeah.
One discrete?
Yeah, that would be an example. That would be an example of an interval like this. But I would say this is the generic interval. This is the interval symbol. And an example is bool, but you could take 0, 1, 2, 3. I mean, that would be an example. There are many finite intervals like this. There are plenty of examples of interval. Okay. But this is not enough to have an interval. You also need, in addition to introducing an interval, once you have introduced an interval, you introduce these axioms. In other words, these axioms should remain true after the introductions of an interval. Okay? I mean, of course, yeah? Okay, you want these axioms. They are also true. They remain valid even in the presence of an interval. Okay? Of course, if you want to model this, you will not model this into, let's say, a can simple object, but more in double simple object. Okay? So the modeling is not the same thing at the same place, because now you have this interval that you want to model somewhere, and the best way is to model it into delta 1, but not the usual delta 1. It's a new delta 1. Okay? Okay. Okay, so, but in addition to these axioms, yes?
The connection between the interval and the axiom.
For the moment, no. Somehow you may consider that you're just adding an interval in a context, right? So in this sense, there is nothing, no new axiom. It's just a new context, right? But you want to have in the new axiom, which is about this situation. In other words, you want to be able to, okay, so what's happening? Normally, we think of types as spaces. But now, with this type in context, we should think of types as simple types. In this context, types are no longer pure types. They are simple types.
So what is delta 2?
Yes. Delta 2 is the order relation on delta 1. It's half of the square. That's delta 2. So it can be described as, I mean, if you use ordinary notation, you would say that delta 2 would be the set of all x, y in delta 1 cross delta 1, such that x is smaller than y. That's the 2. And for delta 3, you say that it's all x, y, z, so that x smaller than y, smaller than z. So all the delta n are built up actually from delta 1 and delta 2 by this procedure. Delta n is the n simplex. It's all, okay? Okay, where am I? Yeah, so I'm coming back to this. Now that the types are no longer, that's why the title. That's why the title. I say that univalent foundations is polyvalent, meaning that types have a lot of interpretation. They are like blank spaces where you can put a lot of things in there. They don't have to be spaces. They can be anything. Types are anything, really. So they can be, of course, simple types. So everything you have proved about types until now are true for simple types, except that you were not aware that you were proving things about simple types. Well, maybe you were, but okay. Mike Schulman was aware, I suppose. Yes, okay. But now that types have become simple types, we need to distinguish between the constant simple type, which are the pure type, the one we had before. We need to make a difference between the two. It's a strange situation, right? Where types become simple types, but we want to have the old one included in the new one. And that's what this constant inclusion is doing, right? It takes the old one and put it in the new one. So the job that we have to do now, the work that we have to do is to isolate among simple types the constant one, to isolate them axiomatically, okay? And it's very simple. It's very simple to introduce an axiom that does that. It's very much like truncation of types. Simple types can be truncated too. So one possibility is to say that definition, a simple type X is constant if it is orthogonal to well, there are many possible conditions, but I believe I have not completely checked this, but I think it would be enough to say just delta 1. Orthogonal to the map from delta 1, which is the universal simplicial type, to the map from delta 1 to 1 to delta 0. I mean, we have delta. In other words, that means that the diagonal map from x into delta 1 is an equivalence. That characterizes constant simplicial object among all. So you see, that's an orthogonality condition. And we should have some kind of axiom in multi-type theory about, sometimes it's put into higher inductive types, but local objects. Let's call that local objects. Existence of local objects. In other words, if you take a map, like the map from delta 1 to I, and you put this condition here, then the subcategory of those objects is always reflexive. And the reflection here is like E is like the left is like the reflection in this case would be like the co-limit functor, I guess. Yeah. The reflections would be like the co-limit functor. Yeah. But it's not the only possibility. So I'm sorry, e to the delta op. But it's not the only possibility for identifying this subcategory of here the constant is like the inclusion, the inclusion.
So you're looking at this. This is a monad now on the simplicial objects.
Yeah, it's an idempotent monad. It's idempotent monad. Yes, right. Yeah, yeah.
And you're looking at the algebra.
Yeah, yeah, yeah. Yeah, yeah, yeah. But it's not the only possibility. Because we may look at, this is the inclusion of E via the constant simplicial object, but there is another inclusion via the co-skeleton, which is the Cech complex. There are two inclusions. And we can do this one too. This one is about orthogonality with respect to the inclusion I mean, the skeleton 0 of delta n, this is just the union of all the vertices into delta n. And if you ask that the canonical projection into skeleton 0 of delta n is an equivalence, then you're actually asking for x to be the co-skeleton of something constant. And so you can get the other image too. And I mean, if you put axioms which are very much like the truncation axioms, you can get things called skeleton n, co-skeleton n. Skeleton n, etc. And but you need to put some axiom in there, which probably just follow from the existence of local objects. The existence of local objects are enough to give you this construction. Okay. In connection with what I said today, there is a paper by Bertrand Toen in 2005, which is sort of related to what I'm saying today, which is vers une axiomatisation, it's in French, vers une axiomatisation de la théorie des catégories supérieures. In there, he describes axioms that one can put on Quillen model category so that it describes quasi-categories or Siegel categories or complete Siegel spaces and etc. So sort of has a conceptual view on infinity-1 categories. It's on infinity-1. And of course, in there, a very important object is the arrow, the interval. But in his system, the interval does not sit, is not a partially ordered object. It has a different kind of structure. It is a co-category or something like that, etc. So what I'm doing now is different because I'm proposing an axiomatization of simple object, which is sort of different, and to have categories, infinity-1 categories, as some special simple objects. But what's important is that his interval is an H set. It does not say, it does not have H set as such, but his interval, maybe I should write I. There is a map from I to I cross I, and one of his axioms is that this should be a monomorphism from the point of view of homotopy theory. Okay. So it's one of the reasons I believe that to put the interval in H set fits completely with what people in higher category theory have been doing now. Completely. Okay. Well.
It's not the co-multiplication because that would go into the
no, he has a Cartesian, a category with products. It's a category with, it's a diagonal. It's a diagonal, but he says it's a monomorphism from a categorical standpoint. But you want to say that this is an homotopy monomorphism. So what you say is that the following diagram is an homotopy pullback. Homotopy pullback, right? That's the kind of axiom that he is putting. And that makes the interval into H set. Okay. Now, I don't have the time. I guess the picture should be at 11:30 exactly.
No, they'll wait. No.
Oh, okay.
The photographer will wait until they're done.
Okay. 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 I will very briefly sketch the higher category case. I will just do the case of 2, n equal to 2. For infinity 2 category, we should just do the same thing, but not with the same classifying topos, not for classifying an interval, but classifying a disk. We need to classify a disk. So what is the combinatorial notions of a disk? This is a disk, but it's a combinatorial disk. So what is a combinatorial disk? Well, this combinatorial disk, first there is a projection to the interval. So a combinatorial disk is an interval, a 2 disk with a map. So this is in H set, if you like. So these are 2 sets. The codomain has the structure of an interval. And the fibers have also the structure of an interval. So you can say that this object D over I is also an interval. So it's a family of intervals. Okay?
Even at the end?
I'm sorry?
Even at the end?
Good question. You will have 2 sections, S0, S1, the upper sections and the lower section, okay? And now the equalizer of S0, S1, the place where they are equal, so you take the equalizer in categorical term, right? We are in H sets. That should be 0, 1. In other words, the 2 sections, or this family of intervals, degenerate exactly at the endpoints. Exactly. Okay. Well, there is a topos classifying that. The objects are maybe called cellular sets. I don't have the time to put the details. And there is a notion of 2 category in there, etc. And that's the notions of infinity 2 category. And this is related to a paper, if you want, of Clark Barwick and Chris Schumer Dries. It's called On the Unicity of the homotopy theory of higher categories. In other words, they do for infinity n categories what tau n has done for infinity 1 categories. Okay? And in the case n equal to 2, the basic object is a 2-cell, an abstract 2-cell. But if you look at it very closely, you'll see that this 2-cell has the structure of a disk, exactly as I described. And you can repeat what you have done for simplified set for pre-sheaves on the classifying topos for that, I would say. Okay, this is very sketchy. I'm sorry, the time is short. I would like to say a little bit something about spectra, because there is something interesting there, which spectra. I recall that the spectrum is a sequence of space, each equivalent to the loop space of the next one. So that's what a spectrum is. It's a family of spaces, of pointed spaces, having this property. And that plays, of course, an important role in topology. And people, I mean, Eric, for example, gave a talk on the Allenberg-MacLane spectra. And they play a very important role in topology, and they are more like abelian groups. Now, I would like to state a result which I find very surprising, and which I learned from Georg Biedermann. In 2007, there was a conference at the Field Institute, and we had a private discussion, and he told me that. And I will say, and also it was independently discovered by Charles Rex. In 2008, in a talk in Barcelona, he also pointed out what I'm going to say. So I guess we should say theorem. The category of bundles of spectra is an infinity topos. So what's a bundle of spectra? It's a family. You have a base B, It's a family of spectra parameterized. So it's a bundle of spectra. So each spectrum has a zero section. So there is a zero section, etc. And there is a notion of a bundle of object in a category. The category of spectra is an infinity-1 category. And each time you have an infinity-1 category, you can consider another category, which are bundles of objects in this category. It's like categories of families of objects in this category. Now, take the category of spectra and look at the category of families parameterized by Euler spaces, and it's an infinity topos. Why is that interesting? Well, I'm sorry? Very good question. Very good question. What does it classify? I didn't know until I came here and discussed with Eric Finster. We had a discussion and we came to the conclusion. So I guess I could say it as a theorem, maybe. So Biederman is involved in these discussions. That this topos, it classifies stable objects. In other words, what is a stable object?
My question was, what is the object classifier in the topos?
Oh, good. Yeah. Yeah.
So that's, let's say
That's very interesting. Yeah.
That P is a point. Then we
Yeah.
just have a usual spectra.
Yeah.
So then we have a spectrum,
Oh,
which is the base of the universal
yeah.
family of spectra.
Yeah. Well, it has something to do with the fact that you can construct extensions. Because group extension is a parameter space for all extensions. So you have to sum up over all extension with a given fiber. It has something to do. It's kind of bizarre. I mean, it's, for example, even the hum object in there, what's this?
No,
Exponent?
is clear. Internal form in Spectra is not a problem.
But
Well, it doesn't matter. Bundle Spectra.
yeah.
That I don't see a difference, but I totally don't see the object classifier.
Okay, the universal, the universe. What is the universe in this topos? Yeah, yeah. I thought I don't see it clearly, I must say. I think it's it has something to do with the fact that you have X. But I will say a few. Okay, look, this is very mysterious. But the topos itself, let's call that I don't know. Should be given a special name, maybe BS for bundle of spectra. Okay, so it classifies stable object. It means that in there is. I'm sorry.
That's an unfortunate notation. How about SH or something?
BS is not good. No. Okay, I'm sorry. It collides with something else.
It collides with the English vernacular.
Oh. Okay. What about?
How about SH? It's stable homotopy.
Oh, okay. SH. Okay. Why not? Okay. SH. Okay. Okay. Fancy. Okay. SH. Okay. Okay. It classifies stable objects. So what do I mean? It's exactly like Simpliciter sets classifies an interval. It's sort of generated by an interval. This topos is generated by one object which is stable. And that's an interesting thing because we have not met stable object until now in homotopy type theory. As an object, a pointed object, so you have a X, a type, a P, a base point. That's about the only thing I can write in.
May I interrupt you for a second again? So when you're saying that the category of bundles of spectra, do you mean fixed B or
No, variable B.
Oh,
Yeah.
then SH probably is not such a great idea.
Oh, yes, right, I see. Okay, let's put a hat.
That's indeed something weird.
BUS spec H.
B spec. Yes, B spec. But B is there.
Like this? Why not something like this, okay? Because this hat here means taking families. Or maybe I should take families. Why not family? Family spectra. Okay. That's completely. Okay, so there is a certain object in the families of spectra which is stable and universal. Now, what is a stable object? It's a pointed object such that the canonical map from X to the loop space of the suspensions of X, there's always a canonical map. People have been using that a lot here, is an equivalence. Now, if we look in spaces, there are no such a thing. In Kan complexes, the only stable object is X a point. But in this topos, there is one. And it lives as an object of the topos. Of course, there are objects like this in spectra. Spectra are precisely constructed so that you have this. But the category of spectra is not a topos. You cannot apply directly type theory to spectra because it's not a topos. But if you take families of spectra, it is a topos. Yeah, it's kind of surprising. I don't really understand the consequences of that. But so what is the spatial universal stable object? Because I say it classifies stable object, there must be a universal one. And the universal one is not difficult to guess. It's just the sphere spectrum. I think it's sometimes called S infinity. I don't know. What's the notation for a sphere spectrum? Okay. So you take the sphere spectrum and you as over a point. Okay. So it's just the sphere spectrum over a point. It's a stable object in this category, and this category is a topos. Okay. I would like to finish with trying to sort of explain you why this is true, and I will be over. It may take me 5 or 10 minutes. Is it okay? Okay.
If that board is not your last board, it's a bad one to write on.
I'm sorry. If that, okay. Okay, why is this true? Look, I'm going to introduce a notion of, suppose that C is an infinity one category, pointed. Then, like typically the category of spectra, it's a pointed infinity one category. Then you can do families of C. That's another infinity one category. Definition. C is now is it the name I'm going to put there is it's not definitive, right? I don't know exactly how to call that, but I will say that C is a locus if family of C is an infinity topos. Somehow, if you expand C, you get an infinity topos. So an example of locus, pointed spaces. The category of pointed spaces is a locus. Because what is a family of pointed space? A family of pointed space over a base B is a space with the projection with a section. Okay? That's a family of pointed space. And we recognize here that this is just a diagram of a very simple kind. And the categories of diagrams of this kind form an infinity-topos. It's a pre-sheaf category. Assuming, right, spaces form an infinity-topos. And therefore, these diagrams also.
Isn't it like the Caribbean closure? Because that's just projectors, right?
No, because
No, there's no equivalence.
yeah, it had a lot of objects. You take a family over a base. The Caribbean completion is sort of different.
Yeah, but what's written here is just an object together with a projector on it.
Yeah, but the maps are commutative diagrams, and in the Caribbean completion, the maps are different.
Right.
Right. Okay. This is just a diagram of a certain kind. So a typical example of a locus is the category of pointed spaces. We know that the category of pointed spaces do not form a topos. A topos is never a pointed category. But it is something. It's very close to be a topos. Proof, if you take families of pointed spaces, you immediately see it's a topos. Okay? So, in other words, it's very easy to show that a left exact localization of a locus is a locus. Because that's the definitions of what an infinity-topos is. It should be closed under left exact localization. So left exact localizations of a locus is a locus. So if I take pointed spaces and a left exact localizations of that, I will have again a locus, because pointed space is a locus. See, the left exact localization here is sort of given fiber-wise. It does not move the base at all. It's just a left exact localization on each fiber. Okay, and that produce a left exact localizations of families. It's again a topos. Okay, now not only that pointed spaces form a locus, but any categories of diagrams of pointed spaces. If you have a pointed category, the category of pointed spaces is closed monoidal. With the smash product and harm, etc., it's closed monoidal. So you can say what is a category enriched over that. And if you take now a category D and a category enriched over pointed spaces, then you can form another category, which is the pre-sheaves on it. I mean, the enriched pre-sheaf, the strong functor. So the pointed spaces is again enriched over pointed space. That's a category theorists have been doing that since a long time, right? Taking a category enriched over a category and forming covariant functors, category of a strong covariant functor from functor. So these are all locus. In other words, locus is closed under a certain construction. This is a locus. If you were to take this and then families of, okay. Now, I come to spectra. Spectra are obtained from something called sphere spectra. Is it the name? Sphere spectrum. A suspension spectrum. So a suspension spectrum is a sequence of a space x0, and now you take the suspension of x0, you map it to x1. And you take the suspension of x1, and you map it to x2. The suspensions of x2, you map it to x3, etc. So that's a suspension spectrum.
This is just a spectrum.
I'm sorry?
This is just a spectrum. That thing is a vibrant spectrum, or omega spectrum.
Yeah.
This is just a spectrum.
Okay. Yeah.
Is there a suspension spectrum and suspension spectrum?
Okay. That's correct. That's correct. So maybe you prefer to call that a spectrum and the other a Fabrant spectrum.
That is called omega spectrum.
Okay. That's correct.
And this
Okay.
is just called a spectrum.
Okay.
Some people call this lower one a pre-spectrum.
A pre-spectrum. Okay. That's the same. Okay. So maybe it's a pre-spectrum or a spectrum, but clearly there is a passage from here to there. Okay. Now, I want to discuss that, and it will take me just a few minutes. These notions of spectrum is the same as a functor where you have S1 for Hom, x2, S1. In other words, I can create a category. I mean, it's like a sequence of space, but the maps here are not just single maps, they are circles of maps. They are pointed spaces, and in between each, there is a circle of maps. So if you like, you can create a category enriched over pointed spaces where you put the circle as the generators. Okay, that's the diagram D. Okay, that's the diagram. I'm describing here a category enriched over pointed spaces. It is described by, it is sort of free. It's a sequence, and you put for Hom, generating Hom, a circle. And of course, if I were to compose this Hom with this Hom, I will have a 2-sphere, right? So S2, because I will take the smash, etc. Okay? So that's the diagram. And a suspension spectrum or a pre-spectrum, whatever, or a spectrum, is just D into spaces. It is the category of enriched covariant functor from D into space. We have just described in a maybe kind of pedantic way what is a suspension spectrum or a pre-spectrum. It's just enriched functor from this diagram category to spaces. And therefore, this category of kind of spectra form a locus. Okay. This is a locus. Now this is a left exact localization of this one. The category of spectra is a left exact localization of the category of this one of spectra. Why is that? Is that if you have a suspension spectrum, you can construct a new one just by shifting. Is it by shifting? No, looping, right. You see, there will be a canonical map from x0 to omega of x1, and you can have a commutative square like this. This is S parameterized by S1 and x2. You see, you sort of try to stabilize your suspension spectrum so that it become an omega spectrum. But the first step is to move from here to there. by replacing x0 by the loop space of x1. Okay? And now, look, this is left exact because it's a left limit construction. You're taking x1 is a okay. This functor is left exact because omega x1 is a pullback of x1 along itself. It's left exact. And you iterate that and go to the limit. And that's the reflection. And it's classical in topology. That's the reflection. And that shows that the category of spectra is a left exact localization of the category of suspension spectra. And therefore, the category of spectra is a locus. Therefore, families of is an infinity-topos. This is just a rephrasing. I mean, the proof by Biedermann of this result is via Goodwillie calculus. I mean, it comes from understanding what is a linear functor for the Goodwillie calculus, and Goodwillie calculus sort of generalized that. And there are polynomial functors. This is going from linear to polynomial functors. And I think I should stop here. And maybe in some near future, maybe Eric would be happy to give us a little something about Goodwillie calculus in some, that would be nice. I should stop here. Thank you very much. I'm sorry for